Hello, my name is Tanmay Gupta and I'm here to present our work on general purpose vision systems. Today, computer vision models may be described as n-purpose models. This includes task-specific models such as our image classifiers, depth predictors, and image segmenters, as well as multitask models such as Mask-Arsanin and Wilbert 12-in-1 that are designed and trained for a pre-selected set of tasks. However, these n-purpose models are difficult to extend to new tasks, especially if the new task requires a new output modality. In this work, we aim to move towards general-purpose models that can not only be trained on a large number of tasks, but are also easy to adapt to new tasks. To make the goal more concrete, we formalize the three tenets of GPV to serve as guiding principles. The first tenet is generality of architecture, which states that a GPV should support learning a wide range of tasks within a broad domain without requiring any change to the architecture or the learning algorithm. Here, we take inspiration from biological GPVs. With a limited number of inputs and output modalities, we humans can accomplish an astonishing range of tasks in the real world. Our GPVs should be able to do the same given the right interface with the world. The second tenet is generality of concepts across skills, which says a GPV should be able to perform tasks in novel skill concept combinations. This principle suggests that if a GPV has been trained to answer visual questions about dogs and localized cats, then it should now be able to answer questions about cats and localized dogs. That is, concepts learned in context of one skill should be applicable in context of another skill. The third tenet of GPV is generality of learning. This states that a GPV should be able to learn new tasks with minimal loss of performance on previously learned tasks. It means that a GPV trained to localize cats should now be able to perform a related but novel skill, such as referring expression grounding, where the goal is to localize a specific instance of cat, like the brown cat. Our work makes progress towards addressing each of these tenets. We introduce GPV1, a task-agnostic vision language architecture that can be trained on any task that takes an image and text as inputs and produces text and bounding boxes as outputs. For example, the prompt "generate a description for the image" produces the caption "a dog and a cat lying on a bed," and the prompt "locate the dog" produces the bounding box around the dog. To demonstrate the generality of GPV1's architecture, we trained it jointly on 4 tasks: localization, classification, VQA, and captioning. The architecture itself consists of image and text encoders based on DETR and BERT, Wilbert's co-attention module for cross-modal fusion, and modality-specific decoders for boxes, region-relevant scores, and freeform text. Note that the text decoder is reused across tasks like VQA, captioning, and classification. To evaluate generality of concepts across skills, we created a new split of COCO, which holds out certain skill concept combinations during training, and then explicitly evaluates the performance on these unseen skill concept pairs. First, we retrain and evaluate existing specialized models for each skill. The table on top shows performance on concepts seen during training for each skill, while the bottom table shows performance on concepts not seen in skill training data. We observe that performance on unseen concepts is significantly lower than seen. When GPU1 is trained on each of these tasks separately, it achieves similar performance to specialized models. However, joint training leads to significant gains, especially on unseen skill concept combinations. To evaluate generality of learning, we evaluate performance on the zero-shot referring expression task, as well as analyze GPU1's learning efficiency and robustness to forgetting while learning the new referring expressions task. I would now like to conclude by highlighting the GRID benchmark, which is a follow-up work that aims to vastly improve and simplify the evaluation for GPVs. Specifically, GRID evaluates the generality, robustness, and calibration of vision models across 7 tasks, multiple data sources, and a large and diverse set of concepts. With that, I thank all of you for your attention.